Hello, my dear students, friends. How are you? Fine? Very good. Today we are going to discuss uses of potentiometer. Okay. In the previous video, we have understood what is the basics of a potentiometer, what is its principle. Okay. And today we are going to discuss basically three of its uses. Okay. This is the topic uses of potentiometer coming from the chapter current electricity. Okay, chapter number 3 of class 12. I hope you are ready with your pen and page. Okay, so that you can get all these things get copied on the from the board. Okay, what is a potentiometer? First, we need to understand what is a potentiometer. I have already discussed. It is simply a wire of about 4, 5, 6 meter long. Okay, this is a driving cell, and these are some metallic strip. Okay, so the resistance is 0. Metallic strip, resistance is 0. This is the basic figure. Okay, potentiometer. Are you getting? And if you want, you can put one resistor here. Okay, good. So this point is A, this point is B. Okay, in the real practice, this 4-5 meter wire is kept this way. Okay, to reduce the dimension of the that one apparatus. Good. Now, what are the uses of it? First use to measure the value of unknown EMF. Okay? To measure the value of unknown EMF. It means to measure the EMF of unknown cell. You can write that way also. To measure the EMF of unknown cell. Second, to compare the EMF of two cells. If you have two cells, then we can compare their EMF using this potentiometer device. And the third use, to measure the internal resistance of a cell. Okay, what is the internal resistance? It is a cell. If current passes through the cell, the current gets some obstruction in the inside the cell itself. That obstruction from the cell itself is called internal resistance. Okay, so this is the cell. We put a small resistance in series nearby it, so that is called internal resistance. So we are going to find out the value of internal resistance using a potentiometer. Okay, basically there are three uses. First, we do measure the EMF of the cell. Okay, I hope you copied all these things. Then we are going to explain the first use of it. In fact, the first use was little bit explained in the last class itself. Okay. Say I have one cell whose EMF is not known. This value I don't know. It has some internal resistance. Okay. Now what I need to do, I need to put this setup. I need to put this, connect this with the potentiometer wire. How? Connect the positive terminal of the cell with the positive terminal of the wire. Okay, this is positive, no? And the negative terminal of the cell through a resistor and a galvanometer. Connect to a jockey and place the jockey here, and which can be slided over the wire. Are you getting my point? So this is the basic setup of potentiometer to measure the EMF of unknown cell. Are you getting my point? So as you understand here, potential gradient is equal, this is the V, are you getting my point? And the potential difference between A and B is say VAB divided by length. Potential difference divided by length is called potential gradient. Are you getting my point? So if the jockey is placed there and the galvanometer is showing deflection, it means the potential difference between A and P because of this volt. As you understand, you see, say this is a 10 volt battery. It means the potential difference between this point and this point will be 10 volt, and potential difference between this point and the midpoint will be 5 volt. The potential difference between this point and this point will be somewhere less than 5 volt. No? We have to do it by unitary method. No? If the potential gradient means voltage drop per unit length is constant, we can easily do it by unitary method. Okay. Say at any moment galvanometer is showing deflection, it means current is flowing there. It means VAP is not equal to EMF of the cell. No? VAP is not equal to EMF of the cell. Either this is greater or the potential difference between these 2 points is greater. That is why current is flowing. So what I need to do, I need to shift the jockey. Say jockey is shifted to this point. Say the jockey is shifted to this point. And again I see the deflection of the galvanometer, say in the opposite direction. Say what it means, I have to shift the jockey towards left. But you have to adjust the position of the jockey in such a way that no deflection on the galvanometer is found. No deflection on the galvanometer is found. Okay. Once you get no deflection, it means no current is there. If no current is there, means potential difference this point, these 2 points, and the potential difference these 2 points will be same. Say this is something say Mn. It means for no deflection condition, VAP means potential difference between A and P must be equal to potential difference between M and N. Are you getting my point? It will behave like 2 battery of same voltage and same polarity. So no current will be there in the resistor. Here the R is the galvanometer. Okay. Okay. Now you see what is VAP. Potential difference between A and P. So this length is X, means null point you are getting at a distance X from the left gap. What is VAP? It is nothing but potential gradient VAB by length into X. Are you getting my point? Potential gradient into length. It is the potential difference between A and P. And what is VMN? The potential difference between these 2 points can be written as EMF of the cell. Why? As you are measuring the potential difference when no current is flowing. When no current flows through the battery, the potential drop inside the battery is 0. It means the potential difference across the terminal of the battery is nothing but the EMF only. Are you getting it? That thing already you have discussed. What is EMF? What is terminal voltage? So now the potential difference between M and N is nothing but EMF. So simply by this expression VAB by L into X, we can calculate the EMF of the cell. You see, potential difference between this point and this point can be easily calculated by one galvanometer, a voltmeter also. Length, total length of the wire you have chosen, and X by shifting the jockey you are finding it, na? And we have already some scales over which the wire is there, na? So from the scale reading only we can easily find out the X. Okay. If this external resistance is not there, if it is not there, the potential difference between A and B will be V itself. So you can put there V also. Are you getting? But if there is some external resistance to control the overflow of the current, then here we need to put VAB, na? Potential difference between A and B. In fact, potential difference between A and B you can calculate by numerical method also, na? If the resistance is given, if the whole wire resistance is known, you can find out the current in this branch minus the voltage drop here. Whatever will be left, it will be the potential difference between A and B. Are you getting? So this is the simple way how we can measure the unknown EMF of a cell. Are you getting? Very good. Then let me go to the another method, that one by comparison of EMF between two cells. But remember, in this method there are some limitations. Okay, what are the limitations? See, you can see here, this is the potential difference between A and B. Are you getting my point? This is the length of the wire. If the length is not properly measured, okay, if the length is not properly measured, because while to knot the that one wire also with that metallic strip, small amount of length is required to put the knot. Are you getting my point? There may be some end corrections. Are you getting? And one more thing, we are assuming that the metallic strips are having no resistance, okay, but in real practice it has some resistance. Are you getting my point? So in that case, actually whatever potential gradient you are getting, it is approximated value only, it is not the actual value. Are you getting my point? So it means if the potential gradient is approximated value only, and x is also a little bit approximated because you are not calculating that end correction, that EMF will be nearby correct, that is not the actual. Okay, so it means it has some error while measuring the EMF through this setup, you are going to get the approximated value but not the actual value. Okay, to overcome this type of trouble, we are using that second technique to compare the EMF between two cells. Okay, rub it. I need to rub it these things, and I hope you have copied. Let me go for the second part. Second part is to compare the EMF between two cells. To compare the EMF between two cells. Okay, what I do here, say I have two cells, this is U1 and one another cell of EMF E2, internal resistance R2. Okay, let me connect it parallelly. You need to draw it once more, the whole figure you need to draw it. Okay, they are parallel. Now let me apply switch here. Okay, let me apply switch here, that is S2, that is S1. Okay, S1, S2, E1, R1, S1, E2, R2, S2. What is E1? EMF of the first cell. What is R1? Internal resistance of the first cell, though it has no use of this mechanism, but still internal resistance is there. What is S1? Switch in the first circuit. What is S2? Switch in the second circuit. But you see, if S1 is on, it means this circuit will be on work. If S1 is off but S2 is on, it means this bigger circuit will be working. Okay, good. Now please try to understand. Say initially I just close this circuit. Okay, it means I just on this switch S1. S1 is switched on now. Now this circuit will be working. If the value of E1 is more, then you can expect null point somewhere away from the point A. If the value of E1 is less, you can expect the null point little bit closer to A. That thing we have already discussed. More will be EMF, more will be the balancing length. It means more will be the EMF, more will be the balancing length. They are directly proportional. More EMF, more balancing length. If you equate it, you can find some constant. Are you getting my point? Now you see, if I off this switch S1 and on the switch S2, then again more will be EMF, more will be the balancing length, less will be EMF, less will be the balancing length. So you can compare from this expression. You can find out E1 upon E2 equal to X1 upon X2. Therefore, if you compare two cases, E1 and E2, more will be the E1, more will be the X1, more will be E2 and more will be the X2, and vice versa. Are you getting? From this expression, you see, you are comparing actually the EMF. Out of these two cells, that is driving cell, that is different issue. But these two cells, if you know EMF of anyone, you can calculate the other. Say you know E1, E2 can be calculated, because X1 and X2 will be easily visible on the potentiometer bridge only, na? Because you are finding that balancing length by your experimentation. The value of X can be easily found, means X1 and X2 can be found out of E1 and E2. If anyone is known, the other can easily be calculated. Are you getting my point? So you can write this expression, say E2 you know, so E1 equal to what? X1 upon X2 whole into E2. So from this expression you can find the value of E1, which is unknown. E2 was known. Are you getting my point? So this is a method by which we can compare two cells. Why it is the superior method? Why it is a better method than the measurement method? Because you see in the previous figure that was E equal to V by L into X, and error was there. Error was in this quantity. You see, E equal to something into X. That is something is nothing but the potential gradient. And taking the ratio, I have just nullified this quantity which contains some error. Okay, because I am taking the ratio, so ratio here also it will be there, here also it will be there. We can cut it down, So it means this is a better method because error is not there, While comparing, the error goes out of the picture. So that is why it is a better method. Now what I do, I am going for the third use of potentiometer. What is that? To know to measure the internal resistance of a cell. Okay. Again I have to rub it. I think you have copied all these things. If not, put a pause and write it first. Then come to the second part. So let me rub it. The third use. To measure the internal resistance of a cell. Okay, I have to redraw this figure. Okay, I'm just editing here only, but remember you have to draw it once more. Say this is a cell whose EMF is known, but its internal resistance is unknown. Okay, then this is galvanometer, then this is jockey, this is galvanometer. Okay, to detect the current. Are you getting my point? Very good. Now put one another resistance, capital R, parallel to it, and give a switch here. Okay, good. So in this figure we have to see it properly. If S is off, no current will be passing in this circuit. if S is off, no current will be flowing through this branch. Okay, I will be 0. And if X is the balancing length, no current will be flowing here also, because for balancing length galvanometer shows no deflection, because this potential difference and this potential difference will be equal. Are you getting it? Say this is M, this is N, this is A, this is P. If S is off for balance condition, V of Mn, it means potential difference between point M and N equal to potential difference between A and P, and potential difference between Mn is also called EMF, and VAP is nothing but again potential drop per unit length into X. Are you getting it? You can say that this is equation number 1. Okay, now you do one thing. Remember, no switch is there. If S is on now, if S is on, remember S is on means this circuit will work as well as this also work, because already it is connected, na? No switch was there. So now current will be flowing. For balance, now again I need to search the balancing length. Say I find the balancing length here at some x2. Initially it was at some x1. Now you see, if I get the balancing length at new position x2, no current will be flowing through this cell. Is it correct? Or no current flowing through the galvanometer? It is correct. Actually, as the galvanometer is showing no deflection, it means no current is flowing through this. But it does not mean that no current is flowing through the cell, because in the initial cases, in the previous condition, this switch was off. So if here is current, that current must pass through this. But here there was no current beginning in the previous case. But now you see, in this case, current is not there in the galvanometer, but this circuit is working. You see, from the cell to the external resistance, this circuit is working. Though there is no current in the galvanometer, but current is there in the other circuit. Are you getting my point? This is very important. Initially this circuit was off, but now this circuit is on, so that is why current is there. As current is there, it means current is flowing through the cell. Though the galvanometer current is 0, but current is flowing through the cell. Current is flowing through the cell means cell will drop some voltage inside it. Cell will drop some voltage inside it means the potential difference across the terminal of the cell is not now EMF, but little less than EMF, which is called terminal voltage. Are you getting my point? Good. That is the point I am going to discuss. See, if S is on for balancing condition, the potential difference between M and N must be equal to potential difference between A and P, new position of the point. Okay, yeah, P dash you can write. Say this is P dash. Initially it was at P, now it is P dash. Now I have to write here VMN. What is VMN? Can I put now VMN as E? No, because initially no current was flowing through the cell. That is why these 2 points, potential difference between these 2 points is called EMF. But now current is flowing in the circuit. It means the potential difference between VM and N is called terminal voltage. VMN is not EMF now. VMN is terminal voltage equal to VAP dash. What? again potential gradient into new length x2. Are you getting? This is equation number 2. I am repeating better. What is E? EMF. What is V? Terminal voltage. Okay. If required, you can write also. Na? You write VT, terminal voltage. Okay. Now from 1 and 2. From 1 and 2. I get 1 and 2. I get E upon Vt equals x1 upon x2. Can you say whether x1 is more or x2 is more? Think and say whether the length, balancing length x1 is more or x2 is more. Whether balancing length in the earlier condition is more or in the second condition is more. Yes, answer is x1 greater than, here x1 greater than x2. Why? Because x1 balances EMF, x2 balances for terminal voltage, and I understand terminal voltage is little less than the EMF na? When the cell is discharging more. Okay, so that is why for that corresponding balancing length also should be little less. So this thing you should note. Now you see, our aim is to find out the internal resistance, means R, but up till now I have not developed any relations which contain a smaller. Are you getting my point? Now I am going to convert this ratio EMF by terminal voltage in terms of internal resistance. So for that you need to put this equation number 3. Okay, you can put it as equation number 3. Again we know, say this is a cell, this is internal resistance and that is external resistance. For this circuit you know EMF equal to voltage drop inside and voltage drop outside. Total EMF equal to voltage drop inside and voltage drop outside. You know this thing, EMF. And what is current? If I current is there, I current can be written as terminal voltage divided by resistance. Are you getting it? And you can put this equation as V, take the V common, it means it is R by R plus 1. Okay, from this expression you can write E upon V. Here V is terminal voltage. Okay, V is terminal voltage. From this equation you can write E upon Vt equals R upon R plus 1. Are you getting it? This is equation number 4. Now comparing 3 and 4, we are going to get the relation. Okay, comparing 3 and 4. Okay beta, let me rub this figure. It is already with you. I think you have already copied. From 3 and 4, from equation 3 and 4. What is 3? E by Vt. What is 4? E upon Vt. It means x1 upon x2 equals this one. Okay, so from that I can get R upon R equal to x1 upon x2 minus 1, and from that I can get x1 upon x2 minus 1 whole into R. So this is the expression from which you can calculate the internal resistance of a cell. Okay, what is the external resistance? You have applied na, parallel to that cell whose EMF is E. Okay, that is, you know, x1 and x2 is found by experimentation. One time I have balanced for EMF, second time I have balanced it for terminal voltage. So this is the small r is the internal resistance. Okay, so we can apply this for mathematical problem solving. Good. So these are the basically 3 uses of potentiometer. Again, first to measure the EMF of cell. Okay, this method has some error because of that and corrections. So better method is, second method is that one to compare the EMF of 2 cells. Okay, and third use of potentiometer is to measure the internal resistance of a cell. Okay guys, thank you, keep studying.